What if I told you almost every explanation of Newton's cradle you've heard is wrong? Let me show you why. You lift one ball, release it, and then watch in awe as the last ball on the opposite side swings away, seemingly transferring its energy perfectly to the last ball. But there's something almost everyone gets wrong about this toy. Almost every explanation you'll find online tells you the same thing. This works because of the conservation of momentum.
For example, if one ball is released, one ball will come out the other end, conserving momentum.
And on the surface, this makes sense, right? Momentum is always conserved. So if you lift one ball, it'll strike the others and voila, the last ball flies off with the same momentum. So it's conservation of momentum that makes the last ball fly off instead of making the others move, right? Now I've added a tiny piece of plastic in between two of the balls. It doesn't change the mass significantly, but it'll likely absorb some of the impact, maybe making the last ball not pop off so high. But let's see what happens. So instead of one ball popping off the end with all the momentum, all of the balls move as one mass together. In this case, momentum is still conserved because momentum is mass times velocity. So we start with a large velocity and a small mass, and this gets converted to a small velocity with a large mass. So momentum was still conserved in this case as well, but it didn't make the end ball pop off. So something else is going on here in Newton's cradle. To see what's happening here, let's start with just two balls. Imagine we have two balls of equal mass. One strikes the other. Now we have two key principles that should tell us what's going to happen to the velocities of these balls after the collision. First, the conservation of momentum. The momentum of ball 1 plus ball 2 before the collision will equal the momentum after the collision. And the second is the conservation of energy. The total kinetic energy before the collision will equal the total kinetic energy after the collision. So that means the only unknowns are the velocities of both balls after the collision. We can solve for these, and what we get is that ball 1 will come to a stop and ball 2 will move off with the same velocity that ball 1 had before the impact. This is the classic Newton's cradle explanation. And it works, but only for two balls. What happens when we add a third ball? Now we still only have two equations, but now we have three unknowns with the added velocity of the third ball. When you have two equations with three unknowns, it becomes unsolvable. There are infinitely many possible answers. Yet the Newton's cradle seems to always know what to do, no matter how many balls we drop. Now you might try to break it up and imagine each collision happening one by one. So the momentum from this ball gets transferred to this one, 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 and then the end pops off. But that would only work if all the balls had a separation between them. In real life, all the balls in the cradle are in contact with each other. So momentum transfers almost instantaneously. So trying to separate these into individual collisions isn't correct. As Nikola Tesla once said, if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. So let's think of Newton's cradle in terms of vibrations. The metal balls might look like they aren't deforming when they strike each other, but on the microscopic level they're compressing, just like a spring. So each ball is acting like a spring with a mass attached to it. What's beneficial about this way of thinking is that we now have an equation that relates the force on each sphere to the displacement of each sphere. So that means that we can now solve a set of differential equations to tell us exactly what each ball will do. And what we find is exactly what you would predict. If you send one ball in from the front end, the last ball will pop off, not some different combination of moving spheres. Now the math to get to this point can be confusing, so let me show you what happens without math. And before we continue, I'd like to tell you about our sponsor, BetterHelp. BetterHelp is the world's largest therapy service, and it's 100% online. With BetterHelp, you can tap into a network of over 30,000 licensed and experienced therapists who can help you with a wide range of issues. To get started, you just answer a few questions about your needs and preferences in therapy. That way, BetterHelp can match you with the right therapist from their network. And you can talk to your therapist however you feel comfortable, whether it's via messaging, phone, or video call. You can message your therapist in the app or online anytime and schedule a live session when it's convenient for you. If your therapist isn't the right fit for you for any reason, you can switch to a new therapist at no additional charge. With BetterHelp, you get the same professionalism and quality you expect from in-office therapy, but with more scheduling flexibility and at a more affordable price. So get 10% off your first month at betterhelp.com/actionlab or click the link in the description. And thanks to BetterHelp for sponsoring this video. Now let's get back to our experiment. When the spheres initially collide, there's a shock wave or a compression wave that starts moving through the line of spheres in both directions. So the shock wave that moves to the left reflects and starts moving to the right, and the shock wave that moved to the right eventually reflects and moves to the left. Finally, the two waves meet, and when that happens, the colliding waves force the two balls apart at exactly the contact point, but on the opposite side. So it's almost like the time reversal of the initial collision. The same thing happens with however many balls you start with. If I start with two spheres, then the collision happens further in. But the pressure wave moves through just like before, and the two waves end up colliding two spheres in, exactly mirroring the initial collision. That means that if you mess up the speed of the wave propagation, then it'll change how the whole system reacts. So when I stuck some plastic in between, I slowed down the wave significantly on one side, so the Newton's cradle didn't act like it normally does. What's neat is that using this piece of plastic, you can get the separation to occur wherever you put that piece of plastic. If I lift one ball but have the plastic in between balls 2 and 3, then that's where it separates, or any other spot you put it. If we explain it in terms of these pressure waves, there are reflections that happen anytime it goes from metal to plastic. So this causes there to be a separation point wherever the plastic piece is located. Whether it's 2 balls or 5 balls, the wave propagation is what makes the last balls pop off in the exact order they do. But here's the thing. Even a traditional Newton's cradle doesn't behave exactly as the equations predict. The materials aren't perfect, the balls aren't perfect, they're not perfectly spaced between each other, and the elasticity isn't flawless. In fact, researchers have found that when you start with 1 ball in a 5-ball Newton's cradle, all the balls have movement after the first impact. In a 5-ball Newton's cradle, balls 1, 2, and 3 move backward, while balls 4 and 5 move forward, with ball 4 carrying about 12% of the initial momentum, and ball 5 carrying almost all the rest. What's crazy about all of this is scientists are still working to better understand this simple toy. For example, here's the concluding paragraph from a research paper looking into a more precise model of Newton's cradle. They say, "We've shown that the physics involved in Newton's cradle is far from trivial, and that the standard textbook explanation is only a first approximation. Students should see that apparently simple experiments, when closely examined, can raise a number of complicated questions. One also should be cautious about fully accepting well-established explanations of physical phenomena, without carefully scrutinizing the arguments." So at first glance, Newton's cradle might seem like a straightforward toy, but it's actually a window into a much deeper and richer understanding of physics. So next time you see one of these things on a desk, take a moment and think about the hidden waves of energy that are making it all happen. And thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did, don't forget to hit that subscribe button, and we'll see you next time.